of 8051 microcontroller. So the instruction set, let it be for microcontroller or the microprocessor, the internal operation is going to be same, but the mnemonics and the way how we are representing the instruction, that means the format of the instruction may differ, but the operation is going to be same. Few mnemonics may same, most of the mnemonics will be remaining same. Say for example, if you want to transfer data from source to the destination. In microprocessor also we'll be making use of mnemonic MOV, whereas in microcontroller also we'll make use of MOV only. Like that, most of the mnemonics will be same, but the thing is that the source and the destination registers will be varying. They will be completely varying because the register organization of microprocessor and the register organization of microcontroller are completely different. And here in 8051, in most of the cases, we can make use of all the general purpose registers for the writing of the program. But whereas in 8051 microcontroller, based on the type of instruction, few registers should not be used and few registers should be the destination registers only. So like this, there will be many similarities, but few differences will be there between the instruction set of 8051 microcontroller and the instruction set of 8086 microprocessor. And here, if we move on to the instruction set of 8051 microcontroller, here in a single statement, I can say that all the instructions, whatever the instructions that are being supported by the 8051 microcontroller, they have been grouped into 5 types. All the instructions of 8051 have been grouped into 5 types, and they are named as data transfer instructions, arithmetic instructions, logical instructions, Boolean variable instructions, and the last is nothing but branch instructions. It can also be called as a control transfer instruction. This last one, program branch instruction, or we can call it as a control transfer instruction also. So if you see the names of these instruction types, all these are available for the 8086 also. All these 5 types of instruction sets, they are even available for 8086 microprocessor also. And now if we move into in depth, coming on to the first type of instruction, that is nothing but data transfer instruction. So in this particular data transfer instruction, it is not that if a register is supporting 8 bits of data, if a register is supporting 8 bits of data, it's not mandatory that all the 8 bits needs to be transferred to the destination register, even though you don't require all the 8. Say for example, out of 8 bits, if you want to transfer only 1 or 2 bits, that can be done in 8051 microcontroller. That means you can transfer the data bit by bit, or you can transfer the data, complete data at a time. Transferring is nothing but moving the data from source to the destination. You can do that either bitwise, or you can do it complete data based on the application. So that whenever you are doing the bitwise transfer, that means only when 1 or 2 bits are required, you are transferring only those 2 bits, means the destination register memory space will be low, so that the space can be utilized in a good way. If you are not requiring the remaining 6 bits, but still if you are transferring remaining 6 bits of zeros to the destination, it's a waste of memory space. So because of that reason, the data transfer instructions of 8051 have been developed in such a way that it will be supporting both bitwise transfer as well as it supports the byte transfer also. And another thing is that, as I told you in the beginning, all the registers cannot be used in all kind of instructions, where program counter is one of the general purpose register. Program counter, PC is nothing but program counter, that is the 16-bit register, and it is a general purpose registers. Usually when we talk about general purpose registers, we used to say that general purpose registers are used in developing the programs. But here in data transfer instruction, that means in order to move the data from one place to the another place, that is nothing but from source to the destination, program counter cannot be used. So in a single statement, we can say that program counter is not accessible for data transfer instructions. This is very, very important point that you need to keep in your mind. In data transfer instructions, program counter cannot be used. And if you look into the some examples we have already discussed in 8086, there will be many instructions which will transfer the data from source to the destination. Here I just have listed only three: push, move, push, and here it is pop. Where push and pop, these two are related to the stack register, and move is for the general applications. So this is what about the data transfer instruction set of 8051 microcontroller. And moving on to the next type, next is nothing but the arithmetic instructions. By looking at the name itself, you can say that these kind of instructions are used for performing the arithmetic operations like addition, subtraction, multiplication, division, etc. But here 8051 microcontroller, keep this point in your mind, 8051 microcontroller, it does not support subtraction. That means 8051 microcontroller doesn't have an instruction which can perform the subtract operation, but I'm saying that it is doing the subtraction. And again I'm saying the statement that it doesn't support the subtract, what we call instruction. So here while performing the subtraction, we have two things. One is the general subtraction, and the second thing is nothing but subtracting with borrow. That means considering the borrow as a result, considering the borrow in result. So the arithmetic instructions of 8051 microcontroller, they do not support SUB, but they support SUBB. That means general subtraction is being not performed, or it is not being supported by 8051, but subtraction with borrow, consideration of borrow in the result, that instruction can be supported by the 8051 microcontroller. Here arithmetic instructions means it's not only the plus, minus, into, and division. Here they'll also support increment and decrement. Increment and decrement operations will also come under arithmetic operation only. And here accumulator must be the destination register. Whenever you are performing some arithmetic operations, let it be addition or multiplication or division or anything, the first register, that is nothing but the mnemonic, the register which comes after the mnemonic, the register which comes immediately after the mnemonic must be a register. A is nothing but the accumulator. So accumulator should be used as a destination register whenever you are performing the arithmetic operation. This rule is not there in the arithmetic instructions of 8086. You can make use of any register as an destination register, but in 8051, if you are writing a program for arithmetic operation, accumulator should be the destination register whenever you are doing that add or MUL or div. So program counter, as usually, it cannot be used for arithmetic operations also. So program counter, it cannot be used for data transfer, as well as it cannot be used for arithmetic operations also. And another thing is that it is not going to support compare instruction also. The 8051, it does not have any instruction for comparing the data. And here I have listed few things. See here, MUL A comma B. Here I have taken two examples, MUL A comma AB and DIV AB. If you observe here, I have written a statement like A is compulsory destination. That means accumulator must be the destination register. So if you take these two examples, in these two, immediately after my mnemonic, I have mentioned A. Here my mnemonic is multiplication. Here my mnemonic is division. Immediately after the mnemonic, the register that we call it as a destination register. So in these two instructions, I have taken A as a destination. Not only for these two, let you perform any kind of arithmetic operation. Immediately after the mnemonic, the destination should be accumulator only. And here, what exactly happens when you are writing MUL AB? Whenever you write this particular instruction, before the execution of this instruction, A will be storing the multiplicand and B will store the multiplier. A will store the multiplicand and B will store the multiplier. Let me give an example so that you can understand which one is the multiplier and which one is the multiplicand. Say for example, if I want to perform 222 into 3, I want to multiply 222 with 3. So in this case, this 222 is called as multiplicand. 222 is called as multiplicand, and with whom you are doing the multiplication? With 3. So 3 is called as a multiplier. So before the execution of this instruction, A will store multiplicand and B will store the multiplier. I am repeating once again, before the execution of MUL AB, before the execution, A will store the multiplicand and B will store the multiplier. And after the execution, after multiplying, after the execution means it will perform the multiplication. So when we perform the multiplication, what do we get? We'll be getting 666. So we got the result. So here, how this result is going to be stored and where is it going to be stored? Before the execution, A will have 222 and B will have 6. And after the execution, lower byte of the result. That means if you convert this 666 into the binary form, when you convert this 666 into the binary form, say for example, when you convert this into the binary form, you got 8-bit. That means the 666 is represented in an 8-bit. Of course, 666 cannot be represented in 8-bit. It will take more bits only. Just for your understanding, I am saying that you just assume that your result is having 8-bit. Your multiplication result, when you convert that into the binary, it is of 8-bit. So in 8-bit, how do we represent the bit representation? D0 to D7. So D0 to D4. That means lower byte of your result will be stored in A and higher byte of result will be stored in B. So here you no need to get confusion. Here I have stated two things related to the MULAB. Before the execution of this instruction, A will store the A will store the multiplicand and B will store the multiplier. After the execution, that means multiplication is done and the result is there. So that result, where it has to store, it will be stored again in AB only. So what does A store? A will store the lower byte of the result and B will store the higher byte of the result. So that is about the multiplication instruction. And moving on to the division instruction, division of AB. So here A will be storing dividend and B will be storing the divisor. So I'm just taking this one example for your better understanding. Here 22 by 2. Here 22 we call it as a dividend and 2 will be the divisor. So before the execution 22 will be stored in A and 2 will be stored in B. And after execution means whenever we perform 22 by 2, we'll be getting 11. And 11 and 0 will get. See, what is 11? We call the 11 as a quotient and 0 as a remainder. So generally, we are not bothered about the remainder. When we ask about 22 by 2, what is the result of 22 by 2? We simply say that 11. That means our concentration will be more on quotient, but not on the remainder. But the controller will store both. It will store the quotient as well as it will store the remainder also. Quotient will be stored in A and remainder will be stored in B. So before execution, A will store the dividend and B will store the divisor. After the execution, A will store the quotient and B will store the remainder. So that is about the multiplication and division. Why am I explaining these two in detail? Means remaining all the instructions are as usually how they have been discussed for microprocessor, but these two are little different. Multiplication and division, how we think or how we do with hands in mathematics, that will be differed in while it is being implemented in the processor or the controller. That's why I'm just keeping more concentration on this multiplication and division. And next, see here, as I told you, increment and decrement, they are also considered as arithmetic operations. See here, within how many machine cycles those instructions can be executed. That information I just have listed here. So if you want to, that means if 8051 wants to execute increment DPTR, if 8051 wants to execute increment DPTR, then it requires 2 machine cycles. And whenever it is performing multiplication and division, it requires 4 machine cycles. And for the remaining all, 1 machine cycle. That means multiplication and division operation, they will take more cycles. Taking more cycles means execution time is more whenever you are performing multiplication and division operations. And increment DPTR, while performing the increment DPTR operation, it will be taking 2 machine cycles. For multiplication and division, it will take 4 machine cycles. And for remaining all arithmetic operations, 8051 can execute remaining all arithmetic operations in 1 machine cycle. So this is what about the arithmetic instructions of 8051 microcontroller. And next, if we move on to the Logical instructions. So here there is only one difference between the arithmetic instructions and the logical instructions. Apart from the operation will be different, because here the operands in arithmetic operands, the operands will be add, subtract, multiply, division. Operations are different from arithmetic and the logical, but the remaining things are same. The remaining things are same means here also in logical, uh, one only one particular difference between the arithmetic and logical is that in logical, A is not a compulsory destination. That means accumulator need not to be the first register or immediate to the mnemonic. See here in examples I have mentioned. See this particular example. Here I have written ANL A comma B. So in this case, B is the source and A is the destination. And look at the next example, XOR B comma A. Here A is the source and B is the destination. That means here usage of A is compulsory. If you are taking two registers, among those two registers, one register should be A, but A need not to be the destination register. In logical instructions, A need not to be the destination, but A should be used either as a destination or as a source. But if we come to the arithmetic, in arithmetic operation, A must be used, and that too A must be destination register only. In arithmetic operation, accumulator must be the destination one, but in logical, accumulator need not to be destination, but accumulator must be used. If you are performing an operation between two operands, one operand must be A only. One operand must be stored in A. And if you want to make A as destination, you can make it. But there is no rule that it should be destination. Whereas in arithmetic, A must be the destination. And as you all know, what are the logical operations? A logical ending, logical ORing, logical XORing, logical XNORing. These are all the logical operations. Okay. And here ORL means, here L stands for logical OR. So it has to perform the OR operation between A and B, and the result will be stored in A only. So whatever the register that we represent immediately after the mnemonic, in that register the result will be by defaultly stored. And if you come to this example, here I have written XOR B comma A. So XOR operation will be performed between the content of A and B, and the result will be stored in B. Here in these two cases, result will be stored in A. Here the result is going to be stored in B, because B is the register which is represented immediately after the mnemonic. And here, apart from these three, here I'm concentrating more on these three. See here, RLA, RLC, A. That means rotate left, and rotate left with carry. Here RL means rotate left and RLC means rotate left with carry. So I'm performing the rotate operation for the data which is present in accumulator. Say for example, accumulator contains 8 bits of data. It contains 8 bits. Accumulator contains 8 bits, and we represent generally them with D0 to D7. That means MSB bit is going to be D7 and LSB bit is going to be D0. So here, whenever I say RLA, what will happen? MSB bit, this MSB bit will go and replace the LSB bit. MSB bit, that means whatever the value that is there in D7, that value will be replaced here. That means the D0 value will be replaced with D7, and from here the shifting, that rotating will be performed. But whenever you are saying that rotate left with carry, here also just consider the same thing. 8 bit and 8 bit, we are representing that with D7 to D0. We are representing that with D7 to D0. What will be the result after executing these two? So the result after executing these two will be, in rotate left, the D7 value will be there in the place of D0, and D0 value will be in D1, D1 will be in D2, D2 will be in D3. That is how the rotation is going to be. Okay, but whenever I say RLC, rotate left with carry. So here D7 value will be stored in carry flag place. We have carry flag in PSWR, right? So D7 value will be stored in carry flag. Whatever the carry flag value is there, that value will come and sit in the place of D0, and D0 value will go to D1. D1 value will go to D2. That is how the rotate operation is will be happening. So try to have a clear knowledge or the clear cut a bit difference between these two. Rotate left, only when it is only rotate left, LSB will be replaced by MSB and the remaining bits will be rotating left hand side. But whenever I am saying that rotate left with carry, whenever I am saying rotate left with carry, MSB bit will go and sit in the place of carry flag, and whatever the carry flag value is there, that is going to come and sit in D naught. So here in rotate left, the D7 value, it will move on to both D naught and carry flag. D7 value will move to both D naught and carry flag. Here, whether it is going to carry flag and whether it is not going to carry flag, it's the controller is not bothered whenever you are performing rotate left. But whenever you are performing rotate left with carry, here clearly you are mentioning that involve carry. Then in that scenario, MSB will go to carry flag value will move to D naught, and from D naught the left shifting or the left rotating will be continued. So, and next is nothing but swap A. Swap A. Generally when I say swap, here I just have mentioned only one register. So generally when we say swap, one thing should be replaced with another thing. Say for example, A and B are there. Then A value should be replaced with B and B value should be replaced with A. That means I have to represent two registers. I have to represent two registers. But here I represented only one register. That is nothing but accumulator only. I'm representing one register and I'm asking the controller to perform the swap operation. So then what it will do, as accumulator is of 8-bit register, as accumulator is of 8-bit register, how do we represent them? D naught to D7, D naught to D7. So what it will do when I say swap without mentioning the second register, the lower nibble value will be replaced with higher nibble and the higher nibble value will be replaced with lower nibble. Here you may get confusion, what is nibble? Nibble is nothing but group of 4 bits. Group of 4 bits. As you all know that group of 8 bits is a byte. Group of 8 bits is a byte. In a similar way, group of 4 bits is known as nibble. Group of 4 bits is called as nibble. So whenever I am saying swap and I am mentioning only one register, then the data within that register itself gets swapped. How is it going to be swapped? It will be swapped in such a way that higher nibble will be replaced with lower nibble and lower nibble will be replaced with higher nibble. That means, say for example, 4 ones and 4 zeros. 4 ones and 4 zeros is the input before the execution of swap. And after the execution of swap, lower nibble in 4 ones and 4 zeros is, see, I'll explain you, 4 ones and 4 zeros are there. So here, this is the before execution, this is what the input that A is carrying. So here the lower nibble means these 4 zeros are lower nibbles and these 4 ones are higher nibble. So after the execution, the result will be like this: 4 zeros, 4 ones. That means lower nibble is replaced with higher nibble and the higher nibble is being replaced with lower nibble. So that is what about the swap instruction, or which comes under the logical instruction. And the last point about the logical instructions is that whenever you are working with 8 bits of data, whenever you are performing logical operations with 8 bits of data, then controller requires 2 machine cycles to execute them. And if you are working with less than 8 bits, if you are working with less than 8 bits of data, then to execute the logical instructions, controller will take only 1 machine cycle. So that thing you need to remember. Whenever in logical operations, if you are making use of 8 bits, then processor will take 2 machine cycles to execute them. And if you are working with less than 8 bits of data for the logical operation, then the controller is going to execute that instruction in 1 machine cycle. And the next instruction set is Boolean variable manipulation. So by looking at the heading, you might be feeling like what it is. It's very simple: Boolean variable manipulation. So that means when you look at the word Boolean variable, these two words here, you should understand that these instructions will be dealing with only bits, not complete data. So whenever you want to perform the operation bitwise, then in those scenarios you need to make use of this Boolean variable manipulation. And very important point while you are using this kind of instructions is that carry flag should only be the destination. Carry flag should only be the destination. See, carry flag, it's not a register, it's a flag. Carry flag should be the destination. That means 8051 instruction set, Boolean variable manipulation instruction set will deal only with the carry flag. That means, see here I have written one example, ANL C comma bit. Let this bit value will be 0. As I told you, Boolean variable, whenever you come across the words Boolean variable, the operation will be between the bits only, not between the two data. It will be between the bits. That means within the data, between the bits, the operations are going to be executed, logical operations. And here, as I told you, only carry flag is used in Boolean variable manipulation. So see here, here I am writing ANL C comma bit. I am just considering my bit value as 0. That means here logical and operation should be performed between the value of carry flag and between this particular bit. And similarly, here logical ORing should be performed between carry flag and bit. Bit can be either 1 or 0. And this instruction says clear carry flag. So if you see the three instructions which I have represented here, in these three, the destination is carry flag only. So carry flag should be the destination register whenever you are dealing with the Boolean variable instructions of 8051 microcontroller. See here, for performing AND operation and OR operation for the carry flag, controller requires 2 machine cycles, and for remaining means clear. See, clear, that means clear the carry flag, set the carry flag. For all those instructions, it will be taking only 1 machine cycle. But whenever you want to perform AND operation or the OR operation for the carry flag with a single bit, controller will take 2 machine cycles. And the last instruction set of the 8051 microcontroller is that branch or branch or control transfer instruction. We have discussed this branch or control transfer even in 8086 microprocessor also. So these will be two types, conditional and unconditional. That means control transfer, the name itself is saying that whenever the program is executing the lines of program, so the sequence is going to be disturbed. That means the execution control is going to be transferred from one place to the another place. Instead of to immediate place, it is transferring to the another place. So what are those how those transfers from one place to another place can happen with the help of jump, call, return. With the help of all these instructions, this control transfer, the execution control can be transferred. See here, I told you the control transfer instructions will be of two types, unconditional and conditional. What are the instructions that comes under unconditional? Jump, call, return. Here I am writing address. Here address is simply label. Label name can be anything. Here address I have written it as it is a simple label. That means under this particular label we'll be having some instructions. We'll be having some number of instructions. So in those scenarios, we'll be making use of this jump, call and return. Here I just want to tell you one clear difference between jump and call. So whenever I say jump, the controller will transfer the execution to that particular label where address label is there. That means, say for example, 20 lines are there, and from third line, when it is at the third line, it has come across jump address. When it is executing the third instruction, the controller come to this particular instruction. So here, what is this instruction is saying? Jump ADD RESS. So what it will do? It will jump to the address label. Let that label can be in first instruction line or it can be in 20th instruction line. The controller will transfer completely. It will jump to that particular label. But whenever we have written call, it is not going to jump there. It will call all the instructions which are listed under address to that particular place, and it will execute. So that is the difference between jump and call. Jump means controller will transfer to a label called address. Whenever you are using call, it will get the lines, it will get the program lines which are under the address lines. It is not going to, a controller will not go there. It will get the lines which are listed under the address. So that is the difference between jump and the call. And if we move on to the conditional, that means this jumping or calling or returning or any other control transfer should be done based on the result. Based on the result, if jumping or any other thing is happening, then they are called as conditional control transfer. See here, I have written JC. It has to jump. J means jump. It has to jump. When? If carry is 1. If carry flag value is 1, then only it has to jump, or else it should jump. That means it is based on the result. It is jumping based on the result. So jumping, control transferring based on the result of the instruction. They are called as conditional. So JC means jump if carry is equals to 1. JNC, jump if carry is not 1. JZ, jump if 0, jump if non-zero. So these are all. What about the instruction set of the 8051 microcontroller? So there are many similarities, but only very few differences between the instruction set of 8051 microcontroller and the instruction set of 8086 microprocessor.